Okay. Hello everyone, I'm Yuchen and currently a PhD student at the Institute of Construction Materials at Dresden University of Technology in Germany. Today, I will be presenting to my research titled Deicing of Concrete Pavement with Mineral-Impregnated carbon fibers as Joule heating element. This presentation will be structured as follows. First, begin with the background with controversial deicing methods and the role of mineral-impregnated carbon fiber reinforcement. Second, our methodology and experimental results. Finally, I will outline our version of the digital twins road. And these figures illustrated the core idea of our project, a multifunctional concrete layer enhanced with mineral-impregnated carbon fibers reinforcement. And due to the electrical conductivity of carbon fibers, it enables three key functions. First, temperature sensing, crack detection, and self-heating. Ice formation on winter roads, especially in colder regions, increases accident risks and pavement damage. Current de-icing methods fall into two categories. First, chemical engines, many salts like natrium chloride, calcium chloride, and magnesium chloride are cheap and easy to use, but they penetrated concrete and chloride the steel reinforcement and shortened the structure service life. Second is the mechanical snow remover with poles, works for thin snow, but cannot remove the thin, tightly adhered ice layer. Therefore, new target and sustainable solutions are needed. Mineral-impregnated carbon fiber reinforcements offers a promising alternative. It outperforms steel in terms of strength, weight, and corrosion resistance, while maintaining strong bonding with concrete even at high temperatures, ideal for electrothermal use. Plus, its electrical conductivity enables self-sensing and de-icing functions. A continuous automated protrusion machine was used to impregnate carbon fiber yards with the cement suspension. The continuous carbon fibers first passing through the water bath for preventing and then enters the suspension bath. After passing through several nozzles, the freshly impregnated carbon fibers would onto the weld for about 2 hours. After cutting, the MCFs were curved in the oven and stored for 28 days. Before proceeding with the preparation of ice layer, the Joule heating effects of MCF under different voltages was tested in a constant temperature room. One temperature sensor was attached on the middle of the concrete surface, and one is on the MCF. The figures illustrated that under the high applied voltage, 6 voltage, the concrete surface reached 61 degrees, whereas under 4 voltages, the temperature was around 14 degrees. Similarly, the steady state temperature of the MCF increases from 14.6 degrees at 4 voltage to 17 degrees at 6 voltage, respectively. As shown in the thermal images, even at the limited voltage of 6 voltage, the temperature rises sharply with the homogeneous heat distribution across the entire dampers. As shown on this slide, the damper is kept in a constant environment and features a 5 mm ice layer on the top. To ensure that Joule heating is focused directly at the concrete ice interface, we wrap the 3 sides of the dampers with 20 mm thick polymer strip for isolation, leaving only the top surface for ice formation. Meanwhile, a thermal camera was set up to record the melting process in real time. And all trials were carried out under critical conditions to ensure a fair comparison. Among the different voltage levels tested, the 6 voltage conditions delivered the most impressive performance. Complete melting was achieved in just 52 minutes, the shortest time recorded across all groups. It also produced the most intensive melting area in the final state. In contrast, under the 4 voltage condition, no visible surface changes occurred during the first 30 minutes. Parallel melting only began at around 40 minutes. The full melting took around 73 minutes. Meanwhile, in the reference group, kept at 19 degrees ambient temperature. Each melting didn't start after 90 minutes, and complete melting required as long as 192 minutes. To put this into perspective, the 6 voltage conditions reduce the melting time by 72.8% compared to the reference, a truly remarkable improvement. Building on this de-icing capacity of the MCF, we are now developing an intelligent monitoring system for large-scale components, leveraging digital twin technology. By conducting EFM analysis on our samples, we are able to construct a precise material model. This model does more than just predict the internal temperature field of the materials. More importantly, it enables us to formulate dynamic energy optimization strategy, paving the way for smarter, more efficient thermal management in real-world applications. Our co-worker designed this system for temperature prediction and optimization. As shown on the left, we can configure the input parameters, for instance, setting the voltage to 6. And then we define 2 optimization objectives. First, we aim to heat from 13 degrees to 15 degrees within 600 seconds using a linear voltage increase. Second, we aim to maintain 15 degrees for 1000 seconds with the linear voltage profile. This simulation then runs automatically. Our monitoring target is the central point on the concrete surface. After several iterations, we achieved the first optimization result. And after we got the first optimization result, the process continues with the second optimization, which holds 15 degrees for 1000 seconds. The second optimization's outcomes fully adhere to the preset parameters. The resulting curve is expected similar to what we would anticipate for real samples under same conditions. This model gives us full visibility into the temperature development across all nodes of our samples, with a second-by-second state tracking. This framework allowed us to build a fully automated road control systems. Our final version is to build an automated system that achieves self-de-icing with optimized heating duration and high electrical efficiency. Environmental changes are recorded and measured by the Raspberry Pi equipped with RWTH. The collected data is then transmitted to the analysis model, which calculates the required voltage and heating durations needed to keep the road ice-free. In response, the smart sockets automatically activates and deactivates the systems accordingly. This enables a closed-loop, intelligent infrastructure that can be tested and realized within the Smart Mobility Lab at Dresden, and a facility that will proactive response to weather changes, minimize energy waste, and enhance the road safety. In the end, I would like to thank all my colleagues for their involvement and help throughout these collaborations. And thank you for your attention.